2, 1, let's boogie on. Quadratics, parabolas, and line of symmetry. In this video, I want to go over those concepts, and I want to try to tie in quadratics in this particular chapter, which you study in grade 10. Now, quadratics have this form of ax squared plus bx plus c. Now, a, I guess, is either greater than 0 or it is less than 0. It cannot be 0 because if it's 0, then you would just have bx plus c left, and then that would just be simply a linear equation or a linear expression in this case. Now, where do these quadratics actually come from? So you can see that I drew this cone, and I want to be able to show you that these quadratics, when you take, let's say, a sheet of paper or a plane, just a straight plane, and you try to cut it through a cone, let's say if it's parallel to this cone, you will notice that the intersection where you have your cone and then that plane, that line, you intersect them through. So a little bit off of the center, so either, up, okay, or a little bit behind, okay, that central line, you will notice that you create this wonderful symmetric figure, and that figure we call a parabola. And let me do that, and then once I do that, I will tie in and tell you that that intersection, that parabola, that symmetrical figure, is actually described by a quadratic. And then we're going to take it and we're going to be able to graph several quadratics. Now, those quadratics that we will have, I'm going to show you that they're basically symmetric around kind of the center. And that symmetry goes through a point which is called a vertex. And I'm going to mention these things mostly through just the graphs. And then in a future video, I'll show you how to find these things. And once you have your quadratic, your actual expression, which we're going to turn into a relationship between y and x, so x is your input, y is your output, and then that relationship between them, if you graph it out, there's a nice way of being able to find this line of symmetry in your parabola. Let's see how to do that. And here, so this cone, so notice this cone is an infinite cone. So basically, what you have here, and let's see if I can kind of draw it out. Okay, so this nice cone here, and put it up. Let's now make it so that you have, and that cone continues on. So, it continues on in here, and then, it goes on in here. So it goes on forever. So you have this projection of a cone all the way, okay, that it's going down, like so. Now, the plane that I'm referring to, so if you take a plane and cut it through, so if this is your center line right here, so if I have a center line right here, so if you just go off of the center, if you have this cone, now the cone is three-dimensional, so it's a little bit harder to see here on this plane that I have. But if you took an actual plane, or like a sheet of paper like this, now imagine that this sheet was, again, it's an infinite sheet that we have, and then you just cross it through, so you basically would break this thing up. It would intersect the cone, so if you have a plane, that sheet would just cut right through that cone, and if you would do that, you would have this nice figure which you would be able to create. And that figure, so if you would cut it along, it would look something like this. So this is where exactly the plane and the cone would intersect. So it would look something like that. All right, so let's say that it's intersecting there, and then I'm going to shift it over so it's intersecting there. And so that intersection, so that piece that's kind of cut through that cone, This way, you know, it looks like it's kind of pointing down because our cone is an infinite cone in the bottom dimension. And notice that it's symmetrical, right? It's symmetrical around its center there. And we call this thing, so once we divide it out, we call this a parabola. Now, this parabola can either point downwards because the way that the cone is stationed, it's being flat. But of course, I could have taken this whole thing. I could have taken this right here. Let me copy it, and I can paste it. And I'm going to rotate it around. So if I would flip the cone upside down, like so, then what you would have is, you would have that same parabola, except now it would be looking upwards, right, through that cone. So you can have the cone going down, or you can have the cone moving up. And this is what you would have within. And both are parabolas. Now, one is pointing up and then one is pointing down. This equation that we have, so our quadratic equation, actually describes these parabolas. And you can graph them out. Now, what's special about these is if you take this quadratic, you know, you maybe have learned and have gone through, you know, you can factor it out in many numerous ways, and there's wonderful properties that you have. Now, one of the properties is related to this a. So what happens to this constant a, which is in front of the x squared? So this is second degree because it's a square on the x. That a is, again, either greater than 0 or it is less than 0. Now, if it's greater than 0, it turns out that we have this nice parabola pointing upwards. That's what we have. Now, if the a is less than 0, then what you will notice is, okay, that this parabola is actually pointing downwards. Now, let's take a look at an arbitrarily quadratic. And what I'm going to do is I'm going to now relate it back. So I'm going to create a relationship here between an output y and then this quadratics of ax squared plus bx plus c. Now, let's try to graph it out. So I'm going to take it on decimals, and I'm going to arbitrarily just show you these parabolas and then how they look like. And then you're going to be able to see that there's beautiful symmetry around there. And so let's just say 2x squared. All right, so that would be a is equal to 2. Now, there is no b, right? So bx plus c, so b and c are equal to 0. But notice we have this beautiful parabola, and it's very symmetric. Now, it's symmetric around the y-axis and everything else, so there's symmetry on the left and the right-hand side that you have. Now, as you start putting these values in, so if you have, let's say, plus 5x, and then I'm just arbitrarily shooting these things up, what happens to the parabola? It just keeps shifting, so it just shifts around depending on the values of b and c. But the key idea is that that a, as long as it's positive, our parabola is nicely looking upwards. Now, if I take this and I actually put it and make it negative, so notice what happens. Now the parabola is actually looking down. And that's what I mean with depending on the cone and then that intersection of the plane. But that's one of the properties, which is a beautiful property of these quadratics, is most of the time we study quadratics where a is greater than 0. And the reason is because you can just take out the negative entirely, if you like. You can factor out a -1 and then change that, and then the a can be positive. But if a is negative, then these parabolas are looking downwards. So that's one of the things that you could notice. And it doesn't matter what parabola you have, and it doesn't matter how you play around with these values. So whatever values there are, so notice I set c equals to 0, and then all of a sudden it just shifted, but it's still down. Now, you can also play around and see what happens as a gets bigger and smaller. So notice that in here, and what I'm going to do is, just for the sake of showing this, let me set b and c is equal to 0. And now notice that a is equal to 1. Now if I make a is equal to 2, notice the parabola just gets thinner, right? It gets kind of squished in. If I make it 3, it gets even thinner. 4, it gets even thinner. You know, so let's set it to 10. Notice that it gets much thinner in that particular instance. And that's what happens. That A, okay, either brings the parabola in, okay, or is going to shift the parabola out, depending on the value of that. So if I would make this, you know, the A, let's say 0.1, notice the parabola just kind of opens up, and that's what you have there. And you can do that and continue with that A. But if I made the A now negative, notice it's going to shift it right back down. But the symmetry is still there, right? It's very symmetric around that place. Let's take a look at a few examples to see, you know, where that line of symmetry actually lies. Like, how can we find that line of symmetry? So I'm going to show you that next. So here are 3 examples of quadratics. You have the first one, the second one is a perfect square, and then you have a third one. One thing that I would want you to see kind of right away is to think back, if these quadratics, if you did have to graph the relationship between y and x, then how would they look like, right? Would they open up upwards or downwards? And we talked about that. If A is positive, it's going to look, and it's going to open up upwards. So that means this one should kind of look like that, right, as a parabola somewhere. Now the second one, it's not exactly an ax squared plus bx plus c form, but you can certainly put it if you like, because it's a perfect square. Now for perfect square, that 2x that you see inside there, well, if you multiply 2x times 2x, you're going to get 4x, which is going to be positive. And therefore, this is also going to be looking upwards as well. Now, the last one, notice that the A is actually negative. It's negative 4. So we don't know exactly how it will look, but we know that it's going to look something like this, where the parabola kind of looks downwards, like so. Now, we want to be able to find the symmetry line. You know, where is the symmetry line in between here? And, you know, what I mean by symmetry line is that this line that kind of cuts this through, it almost goes through kind of the middle and then cuts it so that it looks symmetrical to us. Now, this is very hard to see here because I kind of just drew it off by hand. But let's take one of these. So I'm going to take the first one, the 3x squared plus 9x plus 5. And I'm going to graph it back up again. So 3x squared. Let me go back in here. I have y is equal to 3x squared plus, now 9x plus 5, 9x plus 5. And if I graph this, let me not forget here. So there it is. So that's a parabola that we have. I'm going to stretch it out here. And we do notice the symmetry line. Now notice that it is shifted, right? It's not exactly on the y-axis, so it's being shifted. So how do we find this line? Now if we have the graph, then it's much easier for us to figure out, all right, let's try to find out, okay, this kind of middle line that goes through this bottom, which is the minimum point there. Now that minimum point that you see is called the vertex, and we'll talk about the vertex and then how to find it in one of the next videos. Now, so how do we find this symmetry line? So we can see here that it's going to be at negative 1.5, right? That's the x. If we draw it, well, then we can see it, so that's not a big deal. But if we cannot draw it, then what would be a strategy to try to find these? So let me just show you how I approach it. The problem is to find that symmetry line. As you can see, so when I graphed it out, certain values for y just simply don't exist. So notice y at negative 2 or negative 3, negative 4 at the bottom, it's not exactly a relationship, right? So there is no y equals to negative 2. There is no y equals to negative 3. But what we want to be able to do is we want to be able to find points. So we can find and try to find a point, right, for a particular y. So let's say maybe y is equal to 1, and then we can find the 2x values. And if we find those 2x values for here, so I'm going to kind of take an image here, and then I'm going to show you as I'm calculating it out on this. So let me do that, and I'm going to insert it into our work here. So for this, so how do I find this symmetrical line? Well, here it is. That's the actual graph. And what I want to be able to do is I want to find this line of symmetry, which basically cuts this thing in half and goes through that vertex point. That's what I want to be able to find. And that happens at x is equal to negative 1.5 because we saw it from the graph. But if you don't have a graph, then you have to have a strategy to be able to find it. So what I do is, when I work with these, one of the easiest things to do, now there are different methods of doing this, but if you haven't talked about, okay, how to complete a perfect square and how to work with these quadratics, one of the easiest things to do is you will guarantee yourself, if you take your c, so whatever your c is, set your y equal to c. And when you do that, so y is equal to 5, you're guaranteeing, now we don't have this here because our y only goes up to 2 there, as you can see, then it goes upwards. But we're going to be able to go back to that graph and be able to show that. But y is equal to 5 exists. And what I want to find is, I want to find the values for x that actually give me y is equal to 5, which is going to be on the graph. And when I have those 2 points, then from those 2 points, I know that the central line between them, so if I take the average of those 2 points, then it's going to give me the middle point, which is actually, okay, the line of symmetry that it goes through. So that's going to be the strategy. So my first step is, all right, let me take c and set it to y. And that's going to be 5 is equal to, so this is 3x squared plus 9x plus 5. Now, bringing this 5 over to the other side is going to cancel that 5 because it's going to be 5 minus 5, which is 0. What I will have is 0 is equal to 3x squared plus 9x. And now what I'm doing is I'm trying to solve for x. I'm trying to find where does, okay, x belong when y is equal to 5. So I'm trying to find basically the point, right? Now, I can do that because now what I have, I still have a quadratic, but this quadratic is very simple because it's 3x squared plus 9x. I will factor out, for instance, the 3 and the x, and then what I'm going to have is I'm going to have an x plus a 3 left. And notice that what I have now is I'm trying to find what will I substitute for x that is going to give me 0 for this equation. So I'm finding the root of this equation. So it's kind of like the factored form that you utilized for quadratics, except now we've used it for a specific y. And when I do that, so in here, so notice that here I know that x is equal to 0 is going to make this equation 0. So that is one of the values for x. And the other value for x that I will have is if I set x plus 3 and that is equal to 0, which means x is equal to negative 3, those would be the 2 points on the graph at 0 and at negative 3. So my points that I have, so 0, okay, y is equal to 5, and then negative 3, y is equal to 5 are on the graph. That's what I have found by setting my y equal to c. Now, those 2 points, if you take those 2 points and take the average, so meaning you add them up and you divide by 2, notice what will happen is you're going to get your line of symmetry, the point that it goes through. So adding these 2 up, right? So 0 plus negative 3 is negative 3. And negative 3 divided by 2 because that's the average, so that's going to give you negative 1.5. And of course 5 plus 5 is just 10 divided by 2 is still 5. And here is your line of symmetry, right? Your line of symmetry went through negative 1.5. And that's how you can find it always, pretty simply, by always setting your y equal to your c. And when you do that, then you solve for your x. You find the 2 points, and then you find the middle in between them. So let me show you how this actually works on the actual graph visually. So what we have done. Now, of course, we went all the way up to 5, but check this out. So that point, right, 0.5 is what we found. And notice the opposite point. So I'm going to graph that one as well there. So that's the point. Okay, let me do it in this case. So we had 0 and 5, and then we had -3 and 5. And now let's label them right there so that you can see it. All right, so those were the points that we actually found by setting y is equal to 5. We guaranteed ourselves that we would be finding those 2 points by setting y is equal to c. And now the middle, right, so what we had is x is equal to -1.5. So that is that straight line of symmetry, right, so that we found. And that's how you can find the line of symmetry for any of them. This is just one example. Let's take a look at another example how we can find the line of symmetry. What if I had this right here and I have that? Now this one is already, so I'm going to copy this. I already have this in factored form. And when you have it in factored form, then it makes your life a lot simpler. Because if you can graph it, you will see that this factored form is very helpful. Now, however, I do want to show you, okay, that the method that I just used above works for these as well. So I will say expand this out, and if I expand this out, then what I will have is 2x minus 5. That's going to give me 4x squared. So notice that. Then the 2, so times the -5, so it's going to give me -10x. And then I'm going to get -10x again. And then finally I'm going to get plus 25. My relationship is 4x squared minus 20x plus 25. So to find that line of symmetry, right, for any quadratic, it doesn't matter what it is, this is just one method, but it's a useful method. Again, so what I will do is I'm going to take c and I'm going to set y to c. And that's going to give me 25 is equal to 4x squared minus 20x plus 25. The 25, when you bring it over, is going to cancel that 25. That's the reason why I'm setting y to c. And then I have a very simple equation to solve where I can find the roots. So in this case, let me factor out the 4 and the x, and this is going to leave me an x minus 5. And notice that here, so it's always, one of them is always going to be 0, so x is equal to 0. And then here, if you solve that, this is going to be x is equal to 5, right? Because what we're doing is we're trying to find where the equation is equal to 0. So if you bring this over on the other side, you're going to get that. My 2 points, therefore, are 0, 25, and then the other point is 5, 25. Now, if you take the average, because we want to find the line of symmetry, where does it cut this in the middle, you will find that 0 plus 5, all right, divided by 2 is just 2.5. And then that's going to go through. So your line of symmetry is going to be happening at x is equal to 2.5. Let's try that out and see if that's actually true. So I'm going to map this out. This is 2x minus 5 squared. I'm going to go back here to Desmos. Let me remove these. We have y is equal to, so 2x minus 5 squared. Notice this is what it is. Now my line of symmetry, so it's going to go through that vertex point, and notice indeed it was 2.5, right? That's what we did. Now the points that I had found was 0, 25, and the other point was 5, 25. I'm going to label these. Well, that means I have to kind of blow this up a little bit. okay, right there for you. And your line of symmetry went through x is equal to, okay, so that cut it in half, and there's your symmetrical line that goes through the vertex at the bottom, all right, and that goes there. So that line of symmetry is super useful to be able to use. Now, once you know that how to find that line of symmetry, you can always find that vertex as well. And I'm going to show that again through the third example that we have. All right, so those are two examples right here. Here's the last one for you that you can try. And hopefully now with this one is opening up down. So this is our example. So let me copy this, and I'm going to find everything that I need. So let me paste it. And now, so again, what I'm going to do is, okay, so here's my c, so it's -9. So that's what we're going to set y to. And you have your equation now. That -9, when you bring it over to the left-hand side, so these things will cancel. And now you're just solving an equation, which is this. Now you can factor this out. So I'm going to factor out -2x right out. And that's going to give me 2x left there. And I guess this is going to be +5. That's what we have there. And now again, so notice, so my first point, so this is going to be 0, right? So at x is equal to 0. X equals to 0. So that's my first point, 0, -9 on the graph. And then the second point right here, so this is going to give me, so if I solve this, 2x plus 5 is equal to 0. What I'm going to have is that this is going to be negative. So x is equal to negative, and this is 2.5. So that means I have -2.5, -9 as my second point. And now my symmetry line, where does it happen? You add the 2 points and divide by 2 because you want the average again. So this means that x is equal to, because if you do that, you're going to get your line of symmetry at -1.25, and that's also going to be your vertex, which you're going to be able to find later on. And I'll do that in a future video. So let me graph this out. So -4x squared minus 10 minus 9. Let's do that. Y is equal to -4x squared minus 10x minus 9. So notice that it's opening down right there. Now our points that we found were 0 and -9. That's 1 point. So we can see that there. And then the other point was -2.5, -9. And notice the symmetry there again between those 2 points, right there. And our line of symmetry was equal to -1.25x. It's the vertical line right there. So our parabola opens downwards, and that's your line of symmetry. And that's pretty much what you can use. Now, you're going to learn other tools, most likely in grade 10 when you learn quadratics, but that's going to be probably in a later on chapter. But this is a good trick to think about, because you can't always just graph it and look at it. What if your teachers just give you the quadratic and then ask you, like, where's the line of symmetry? So it's good to have some kind of a method. Now, I want you to understand what you're doing here in this method, right? Why am I setting y equal to c? The reason is because then if I set y equal to c, it's going to cancel that c out completely. And then I always have a very simple equation to solve. It's still a quadratic equation, but one of the roots of that equation is always 0, meaning x is equal to 0, which I can factor out. And you will notice that happen in every single example that I just showed you. The other beautiful thing is, by setting y equal to c, you always guarantee yourself that that y exists. It's actually on the graph, because not all y's exist. You can't just take a random y. Now you might be lucky and that y, might be on the graph, but that y may not always be on the graph. So if I go back here, what if I chose y equal to 0? notice that that's not on the graph, which means, you know, you wouldn't be able to find a solution. It would be just kind of playing around there. So it's good to have some kind of a strategy, and this is one of them. All right, so thanks for watching. We'll see you in a future video. Bye, everybody.